a silence so vast it could swallow the concept of sound itself. For billions of years, that silence has endured, unbroken and absolute. The universe has remained a patient void, indifferent to the small blue sphere orbiting its modest star, a planet that dreams, questions, and looks up, waiting for something to look back. And then, one night, the silence changed far across the solar frontier. Beyond Neptune's cold dominion, a flicker appeared, not bright enough to catch the human eye, but sharp enough for a machine, an instrument built to watch the heavens for what does not belong. On a quiet evening in April 2024, the Atlas Survey telescope in Hawaii recorded a motion too deliberate to ignore. Against the eternal black, a faint emerald shimmer moved with impossible purpose, like a whisper crossing a cathedral of stars. At first, astronomers dismissed it. Just another fragment, perhaps a frozen shard tumbling through cosmic drift. One among countless others, tracing ancient, meaningless paths. But as the data began to gather, the illusion of randomness faded. Its speed was wrong. Its vector was wrong. Its story, written in light and mathematics, was not the story of a wandering rock. It was the story of something inbound, the object's path cut through the charted lanes of our solar system with uncanny precision, its trajectory curving in ways no natural force could easily explain. Calculations stacked upon one another, each confirming what the last refused to deny. This visitor wasn't coasting. It was adjusting. Small deviations, consistent and intelligent in their subtlety, began to emerge in its orbital behavior. The numbers trembled with meaning, a pattern in the void. They named it 3I Atlas, the third interstellar object ever observed, a messenger from a star system unknown. But this one was unlike Oumuamua, that brief, tumbling shard that vanished before its secrets could be caught, or Borisov, the comet whose icy breath revealed its natural birth. 3I Atlas carried no tail, no visible rotation, no predictable rhythm. Its body glowed faintly with a spectral green light, a reflection of compounds unfamiliar, a chemistry older than our sun. Astronomers across the world began to refine its orbit. The object's path intersected with Earth's, not by coincidence, not by passing, but by alignment. Its movement seemed too precise, too constant, too deliberate. Like a celestial compass, it pointed toward the cradle of life itself, and beneath the calculations, a quiet unease began to rise. The kind that comes not from what is seen, but from what the mind begins to sense in the spaces between data points. What if this was not a fragment of something dead, but a messenger from something living? What if the universe, in its silence, had finally whispered back? For the first time, humanity looked upon an object that seemed to be looking back. It was not just passing through our neighborhood of stars. It was coming closer in the stillness of scientific rooms, amid the hum of computers and the faint glow of telescope feeds. One question began to haunt every thought, every line of code, every sleepless mind staring at the moving dot across the black. What if this is not an accident of gravity, but an arrival? In the early hours before dawn, when the Pacific sky still clings to darkness, a soft alarm cut through the quiet hum of the Atlas Observatory in Hawaii. It was April 2024, another night of scanning the heavens for faint trails of motion, the kind that revealed the silent travelers drifting across the solar system. On one monitor, a small greenish pixel had shifted ever so slightly between frames, movement so subtle it might have been noise, an echo of light mistaken for something real. But the algorithm did not ignore it. Atlas, built to guard the Earth from unknown wanderers, had seen enough of the sky to know when the stars were lying. Within hours, the alert reached a chain of observatories. Follow-up telescopes from Mauna Kea to La Palma, from Pan-STARRS to the European Southern Observatory, turned their gaze toward a specific patch of darkness just beyond Jupiter's orbit. There, a new point of light emerged, not bright, not stable, but undeniable. It was moving too fast, too free to belong to the sun. Its velocity, more than 40 kilometers per second, was hyperbolic, the unmistakable fingerprint of an interstellar origin. It did not circle our star. It merely passed through its gravity, untouched and unbound. Astronomers had seen this before, but only twice in all of history. The first was Oumuamua in 2017, a cigar-shaped enigma that flashed through the inner solar system before vanishing forever. The second, Borisov, in 2019, was more familiar, a true comet shedding ice and dust, behaving like the countless others born from stellar nurseries. But this new object, labeled 3I Atlas, did not behave like either. It was quiet, smooth, a fragment of motion that seemed to hide its intent. Weeks passed as data streamed in parallax readings. Light curves, trajectory models. The numbers painted a shape of the unknown. It wasn't tumbling, nor flaring with outgassing jets that usually betray the spin of comets. Its reflectivity was steady, metallic almost, as though its surface absorbed light rather than scattered it. But what unsettled astronomers most was the path it chose. As measurements refined, its orbit began to bend, subtly, almost shyly, closer to the plane of Earth's orbit for days. The calculations were rerun, each one returning the same impossible truth. 3I Atlas's trajectory wasn't a passive arc through space. It was evolving. Slight deliberate corrections appeared, too consistent for random gravitational influence. Some suggested it was an illusion, the product of atmospheric distortions or incomplete data. Others whispered of something more. Inside the control rooms, disbelief mixed with adrenaline. Scientists are trained to doubt emotion, to see numbers, not omen. Yet even in their objectivity, a current of unease began to hum beneath the fluorescent lights. They had seen comets wander close before, but this object, from another star, was moving as though it knew where we were. NASA's Jet Propulsion Laboratory confirmed the anomaly. The European Space Agency ran its own models. Independent observatories compared results across hemispheres. Every trajectory pointed toward the same conclusion. If unaltered, the first Atlas would intersect Earth's orbital path within months. There was no reason to panic. Space is vast, and intersect does not mean collide. The odds of impact were infinitesimal, but the precision of the object's path unnerved even the most stoic minds. Its approach was too exact, its velocity too unwavering, its motion too purposeful. In the sterile calm of observatories and research labs, a quiet transformation began. What had started as data points on a screen was now something alive in the human imagination, a story unfolding across light years, a message carried on momentum. Scientists began to stay longer at their desks, watching the thin green line on orbital charts shift fraction by fraction, as though the universe itself were drawing closer to the world that dared to look back. When the official statement was finally released, it was brief, clinical, and careful. Object 3I Atlas has been confirmed as an interstellar body. Current trajectory suggests intersection with Earth's orbital plane. Continued observation is ongoing, but beneath the restraint of those words, an ancient unease stirred, the quiet realization that, for the third time in recorded history, something from the stars had entered our solar domain. Yet unlike those that came before, this one was not passing by. Its course, deliberate and steady, now pointed toward us. And in the vast silence between the planets, an emerald flicker continued its slow descent through the dark, indifferent, or perhaps intent, a silent traveler on a path that defied chance ground-based telescopes soon reached their limits. The object was too small, too distant, and too fast for long-term observation through Earth's atmosphere. Space-based instruments took over NASA's NEO-eyes and the European space agencies, Gaia, observatories, redirected part of their monitoring schedules to track the faint intruder. The data they gathered only deepened the puzzle. The object's surface reflectivity fluctuated slightly, but not in a way consistent with rotation. It emitted no detectable gas, no dust plume, and no clear thermal signature, behavior unlike any known comet or asteroid. Spectroscopic readings indicated traces of metallic oxides and silicate compounds, yet the balance between them did not match materials typical of our solar system. The ratios were off, subtly, but consistently, suggesting the object's formation under different stellar conditions, possibly around a cooler red dwarf or a binary system. Trajectory analysts at the Jet Propulsion Laboratory refined their models using the latest measurements from multiple observatories. The results were clear. 3I Atlas was losing velocity at a rate that could not be fully explained by gravitational deceleration alone. The change was small, less than 1 part in 10 million per second, but measurable. Something was altering its motion. The first possibility considered was out. When comets near the Sun, sublimating ice releases jets of gas that can act like weak thrusters, changing their course slightly. But infrared data revealed no water, carbon dioxide, or other volatiles leaving the object. Its thermal output remained flat. If there were outgassing, it was invisible to every sensor aimed at it. A more conservative explanation was photonic pressure, the momentum of sunlight pushing on its surface. This force is real but extremely weak, significant only for objects with large, thin, reflective areas. The numbers did not align. 3I Atlas was too massive for sunlight alone to shift its path so precisely. Discussions within the astronomical community became more technical and more divided. Some argued the trajectory adjustments were within observational error margins, artifacts of limited data windows. Others countered that the consistency across independent observatories ruled out coincidence. The object's orbit appeared to be small adjustments accumulating into a steady approach that matched Earth's orbital plane within a fraction of a degree. By mid-year, radio telescopes joined the effort. The Very Large Array in New Mexico and the FAST telescope in China scanned the object's coordinates across multiple frequencies. No active signals were detected, but a faint broadband reflection pattern appeared in the returns, smoother and more uniform than those from typical rocky bodies. It suggested a surface density higher than expected for an object of its size, possibly indicating internal uniformity rather than porous, fractured material common to asteroids. Meanwhile, the Minor Planet Center published regular updates to 3I Atlas's orbital parameters. Each revision showed the same direction of correction. Statistical probability placed its next parahelion, the closest point to the Sun, within the same temporal window as Earth's orbit. Not a direct collision course, but close enough to warrant detailed monitoring. Governments and agencies began coordinating through established planetary defense networks. Though the risk of impact remained near zero, procedures required preparedness. Observation time was extended. Near-Earth object tracking algorithms were recalibrated to account for interstellar velocities. The object's predicted closest approach to Earth narrowed from millions of kilometers to hundreds of thousands. For those involved, the experience was both scientific and psychological. Researchers accustomed to detached analysis found themselves watching daily trajectory updates with personal interest. Meetings stretched late into the night, each new data point dissected, debated, and modeled. The situation demanded accuracy, yet every refinement introduced new uncertainty. Satellite networks were scheduled for passive observation. Instruments aboard the James Webb Space Telescope briefly turned toward the object, gathering infrared data across multiple wavelengths. The resulting spectrum showed a sharp, narrow absorption feature near 700 nanometers, a wavelength rarely seen in natural rocky materials. The pattern was unusual but inconclusive. By late summer, global interest had grown. Public statements remained measured, focusing on science and probability, avoiding speculation. Official language described the object as an interstellar interloper exhibiting atypical photometric properties. Behind closed doors, scientists discussed the strangeness more openly. Some wondered if this was simply the universe showing another unfamiliar form of matter, an unclassified mineral, a fragment of a planetary core from another system. Others began to entertain less conventional possibilities. In the data rooms, the focus remained on facts, its distance, speed, brightness, and direction. Each value carried significance, and together they formed a portrait of something that did not fully belong to any known category. The object's hyperbolic path confirmed it was not gravitationally bound to the Sun, yet its steady drift toward Earth's orbital region remained persistent by autumn. The calculations stabilized. The intersection was no longer a matter of uncertainty, it was certain. The question was not if 3I Atlas would cross Earth's orbit, but when and how closely. Estimates ranged from several 100,000 to less than 100,000 kilometers, near enough for detailed imaging once it arrived. It was a scientific opportunity without precedent, a chance to study, in real time, a fragment of another solar system entering ours. Yet the tone in every observatory remained subdued. Data could explain only so much. The closer 3I Atlas came, the less its motion resembled a random journey through gravity's pull. Each small correction, each alignment, reinforced the growing sense that this object followed rules not yet understood, or perhaps intentions still unimagined. By the time autumn shadows lengthened over the northern hemisphere, 3I Atlas had become more than a curiosity. It was an anomaly tightening its path toward the inner solar system, a slow, deliberate intrusion into familiar territory. The numbers continued to shift in subtle, unnerving ways. Small accelerations appeared in the tracking data, deviations so faint that only the most precise instruments could detect them. Yet the patterns persisted. The object was not merely falling through space. It was adjusting itself within it. Solar radiation pressure, gravitational tugs, and outgassing models. All standard explanations failed to account for the measured The values did not fit any known equation governing the motion of inert matter. It was as if an invisible hand were applying gentle, consistent corrections, keeping the object aligned with a precise trajectory. Spectrographic data deepened the mystery. The object's green spectral emission, faint but unmistakable, did not correspond to any conventional chemical or mineralogical profile. Its peak near 532 nanometers resembled emissions from ionized oxygen or certain plasma states, yet there were no surrounding gases to sustain such behavior. The glow seemed intrinsic, radiating directly from the object's surface, oscillating faintly with each passing day. Observers described it as alive with light, though no physical process yet explained why. Theories proliferated, some rigorous, others speculative. One school of thought proposed that 3I Atlas might be a fragment from an exoplanet, a piece of crust ejected long ago by a supernova shockwave. traveling through interstellar space for millions of years before reaching ours. Another suggested it was the remnant core of a frozen comet from a dying binary system, its volatile layers long gone, leaving behind a dense metallic heart infused with exotic isotopes. Yet the observed control of motion undermined both ideas. Natural fragments do not navigate. Even objects with uneven albedo or gas venting follow predictable patterns of drift. This one, by contrast, appeared to respond to the gravitational contours of the solar system with surgical precision. When the sun's pull increased, it adjusted its velocity fractionally, as though compensating. When Jupiter's vast gravity could have perturbed its path, it corrected again, aligning itself back toward the ecliptic, toward Earth's domain. The discussion among scientists grew sharper, less cautious. At the European Southern Observatory, a small team led by orbital dynamics, Dr. Alina Marsic published a paper noting non-gravitational acceleration consistent with directed propulsion. The phrase caused quiet ripples across the scientific community. Within days, NASA's Jet Propulsion Laboratory issued a statement acknowledging unexplained trajectory adjustments under continued observation. The echoes of 2017 were impossible to ignore. That year, the first known interstellar visitor, 1I Oumuamua, had exhibited similar deviations, speeding up slightly as it left the inner solar system. Back then, the data was sparse, the event brief, the object uncapped. Now, however, humanity had a second chance, and this time, the intruder was inbound, not departing. Public interest surged as amateur astronomers began posting nightly updates and raw images. The green object, though still faint, could now be captured through mid-range telescopes as a dim moving star across the constellations. Online forums filled with comparisons to Oumuamua, to comets, to alien probes. Scientists pushed back against premature conclusions, but the tension was already in the air. At observatories, the mood shifted from fascination to unease. The deeper the measurements went, the less the data resembled the behavior of any known natural object. Rotational light curves, the way an object's brightness changes as it spins, showed no consistent period. It was as if 3I Atlas did not rotate at all, or rotated in ways that concealed its orientation. Radar attempts yielded no surface detail. The reflected signal returned clean, featureless, suggesting an extraordinarily smooth structure. Within professional circles, two dominant hypotheses emerged. The first 3I Atlas was a naturally formed body of unusual density and composition, propelled by mechanisms yet unknown perhaps, magnetic interactions with the interplanetary medium or trapped plasma fields from its home system. The second, more daring, implied artificial control, that the object was built or modified to navigate intentionally. Both theories demanded evidence that none yet possessed. What unsettled researchers most was not the data itself, but its consistency. For nearly 6 months, every anomaly had persisted across multiple instruments, agencies, and continents. Nothing could be dismissed as observational error or miscalculation. If it was natural, it was a kind of natural never before observed. If it was artificial, it meant something had crossed the interstellar gulf and found its way to us. In the broader world, the public mood oscillated between wonder and quiet dread. News anchors called it a second visitor, talk shows debated extraterrestrial intent, and social feeds filled with rendered images of glowing stones hurtling toward Earth behind the spectacle. However, the scientific work continued in relentless precision. Every night, telescopes around the planet recorded its position, recalculated its speed, and refined the timeline of its approach. The results converged. Within months, 3I Atlas would enter the inner solar system's heart, a region shared by Earth's orbit. It would not impact, according to most models, but it would pass closer than any interstellar object in recorded history. For scientists, this was the moment to prepare instruments, coordinate observations, and capture data that could redefine astronomy itself. Yet for others, it carried an unspoken tension, a question too fragile to voice. If 3I Atlas truly navigated with purpose, then somewhere in the deep dark between stars, there was intent, and intent implies origin. Something or someone had sent it, and as it drew nearer, reflecting the green light of an unknown chemistry, one thought lingered behind every analysis, every press release, every sleepless night under the cold glow of data monitors. What if this is not just a visitor, but a message? Teams across NASA, ESA, and several university observatories began conducting synchronized tracking sessions. Each session was designed to narrow the object's orbital uncertainty, combining optical and radar data from different latitudes to triangulate its position more precisely. Within weeks, the results showed a clear convergence. 3I Atlas was gradually adjusting its orbit to align even closer with the ecliptic plane, the same flat disk where nearly every planet travels around the Sun. This raised practical questions that demanded engineering-level explanations. Small bodies, especially interstellar ones, tend to maintain random inclinations depending on their entry vector into the solar system. Statistically, the odds of one aligning naturally with the planetary plane were extremely low. The new calculations showed an inclination shift of nearly 1 degree since the first detection, a value too high to attribute to gravitational interactions. Alone, researchers attempted to simulate the motion using standard unbody models that account for solar radiation pressure, the Yarkovsky effect, and other minute forces acting on small objects. None could reproduce the observed course correction. Even the most liberal adjustments, doubling or tripling assumed density or albedo, failed to match the trajectory. It was becoming apparent that 3I Atlas operated under a mechanism that standard celestial mechanics could not easily explain. In the following months, spectroscopy became the central tool. Observatories from Mauna Kea to La Silla captured the faint green emission spectrum again and again. Some teams proposed that the coloration came from metallic oxides excited by cosmic radiation. Others suggested it might originate from trace amounts of ionized nickel or chromium compounds within the crust. However, the stability of the color across varying solar distances contradicted these assumptions. Most chemical emissions would fluctuate as radiation intensity changed. The first Atlas maintained its spectrum with remarkable consistency, even as it crossed zones where solar energy density varied by more than 40%. Parallel to optical work, the Deep Space Network attempted to detect any radio reflections that might hint at structural uniformity. The results were inconclusive. The return signals were faint and scattered, showing none of the roughness or irregular reflection expected from a typical asteroid. The surface appeared to be smoother than any known natural rock, closer to a continuous reflective layer than to regolith or crystalline formations at the Jet Propulsion Laboratory. Modeling teams compared the behavior of 3I Atlas to that of known interstellar objects. Oumuamua had presented a mild acceleration, likely caused by asymmetric outgassing, even though it showed no visible coma. Borisov, the second interstellar object, behaved more like a comet, displaying typical gas jets and dust tails. 3I Atlas fit neither pattern. It emitted no dust, produced no tail, yet accelerated intermittently. The patterns of its motion suggested episodic bursts, as if brief impulses of energy were altering its speed. Physicists considered exotic natural explanations. One proposed that 3I Atlas could contain a trapped magnetic field interacting with the solar wind in unusual ways. Another suggested the possibility of a super-dense carbon lattice structure, generating piezoelectric effects that could create minor propulsion when exposed to fluctuating temperatures. These models remained theoretical. No direct evidence supported them. Meanwhile, the timeline for close approach tightened. Based on current velocities, 3I Atlas was projected to pass within 0.3 astronomical units of Earth, about 45 million kilometers, close enough for high-resolution imaging. Space agencies began coordinating observation campaigns, similar to those used during asteroid flybys, ensuring telescopes worldwide could capture continuous coverage. In media briefings, officials maintained a cautious tone. The language remained strictly technical: non-gravitational acceleration, unidentified emission spectrum, orbital plane alignment. Yet behind closed doors, discussion was more candid. The consistency of course correction data implied a form of controlled movement, whether mechanical, electromagnetic, or otherwise. This did not confirm artificial origin, but it stretched the definition of natural behavior beyond current understanding. Private research groups also joined the analysis. Institutions like the Breakthrough Listen project began scanning for narrowband radio emissions that could indicate deliberate transmission. No signals were detected, but the effort demonstrated how seriously the scientific community now treated the anomaly. As the object drew closer, its visual magnitude increased. By late season, it could be seen through mid-range telescopes as a faint emerald point moving against the stars. Automated surveys reported measurable brightness variations, hinting that the object's surface was irregular or composed of reflective zones. The apparent pattern of these reflections, however, did not match rotational dynamics. It remained unclear whether the variations came from spin or from intermittent luminous activity. The absence of a definitive explanation began to affect scientific communication. Each published paper ended with the same acknowledgement: the observed phenomena remain unresolved. Theories about interstellar debris, plasma propulsion, and exotic chemistry coexisted uneasily, none fully satisfactory. For every new dataset, another contradiction emerged. In the end, the defining feature of 3I Atlas was not its light, its trajectory, or its speed. It was the precision with which it defied expectation. Every calculation reaffirmed that something about it did not belong in the framework of known celestial mechanics. Whether this indicated a new category of interstellar object or an entirely different kind of presence remained unknown. The mystery had moved beyond casual speculation. It was now a formal problem in astrophysics, a case study that could redefine how scientists understood non-gravitational motion in deep space. The deeper the analysis went, the clearer one fact became. 3I Atlas followed no path dictated by chance. Its arrival appeared deliberate, its course exact, its timing precise. Whatever it was coming, and the scientific world was watching every second of its approach. The Atlas system was never built to find miracles. It was built to find threats, fragments of rock, metal, and ice silently threading their way through the darkness, any one of which could end a civilization. Designed by the University of Hawaii and supported by NASA's Planetary Defense Coordination Office, Atlas, the asteroid terrestrial impact last alert system, watched the sky not for beauty but for warning. Its twin telescopes, stationed atop the volcanic peaks of Mauna Loa and Haleakala, scanned the heavens every night, photographing the entire visible sky several times before dawn. In those cold images, the future of humanity could change pixel by pixel. Each frame contained tens of thousands of stars, asteroids, and streaks of light. Software algorithms compared one image against another, looking for anything that moved differently, anything that betrayed motion inconsistent with the slow ballet of the cosmos. Most of the time, these moving dots were catalogued bodies, known asteroids or comets. But every so often, one appeared that was not in the database, a faint, silent intruder crossing the familiar constellations. That night, the discovery did not look remarkable at first. The telescope had recorded a faint smudge near the constellation links, an object only a few pixels wide, dim and slightly offset. The system flagged it automatically, uncatalogued fast mover. But the rate of motion it calculated didn't fit the usual pattern of near-Earth asteroids. Within minutes, the alert triggered a higher priority sequence. The motion was too fast, far too fast to be gravitationally bound to the Sun. Data analysts double-checked the readings. The initial parallax shift between two successive exposures suggested a hyperbolic trajectory, the unmistakable signature of an interstellar origin. Confirmation came from the second Atlas telescope hours later. Both instruments, separated by hundreds of kilometers, registered the same acceleration and the same angle of entry. The software did not exaggerate. It had caught something real, something from beyond the Sun's reach. When the automated system transmitted the alert to the minor planet center, the signal began a chain reaction across observatories worldwide. Telescopes in Chile, Spain, Japan, and the Canary Islands pivoted within hours to capture follow-up data. In less than a night, the faint streak was plotted, and the orbital solution emerged, an inbound interstellar object on a course that would take it directly through the plane of the solar system, close to Earth's orbit, inside the data rooms. Scientists and operators gathered in quiet disbelief. It wasn't the first interstellar object ever found. That honor belonged to Oumuamua years earlier, but this one was faster, brighter, and closer. The designation came quickly. 3I Atlas, the third confirmed interstellar object ever recorded. The name tied it forever to the system that first saw it. Archival footage from that week shows scientists staring at screens, exhausted and mesmerized. They spoke in calm tones, but the silence between their words revealed something heavier than excitement. Discovery in science is rarely pure joy. Often it is tension, the awareness that something new also means something unknown. In interviews later, astronomers described the moment as eerily quiet. The numbers were precise, the instruments flawless, but the implications vast. At such speeds, no human technology could intercept or alter its path. It would arrive and depart under its own physics, unaffected by any will on Earth. And yet, early calculations hinted that it wasn't departing at all. Its trajectory bent slightly inward, cutting close to the planetary plane, a precision too perfect for randomness. Coordination began almost immediately. NASA's Jet Propulsion Laboratory opened real-time tracking updates. The European Space Agency began modeling potential gravitational encounters. The International Astronomical Union confirmed the interstellar classification after only 3 days, a record turnaround. This was no longer just another asteroid watch. It was the beginning of something else entirely, an investigation into purpose. In the following days, human emotion crept quietly into the process. Wonder at the discovery mixed with unease about what it meant. Scientists are trained to separate feeling from analysis, but they are also human, and the idea that something from beyond the stars was entering the same orbital plane as Earth stirred an ancient instinct buried beneath rational thought. It was no longer about data. It was about presence at observatories around the world. Astronomers watched the object's coordinates shift across the grid, line by line, frame by frame. To them, it wasn't a glowing green light or an imagined vessel. It was a precise sequence of numbers and vectors plotted with mathematical rigor. And yet, every new data point drew the same conclusion. 3. I-Atlas was coming closer, and its approach was deliberate. Some called it a cosmic coincidence, others whispered about intent. The official reports remained careful, the language clinical. But in the quiet of those long nights, surrounded by the hum of servers and the faint blue glow of monitors, even the most disciplined minds began to ask the same unspoken question: what if this discovery wasn't about finding a rock, or a relic, or a fragment from another system, but about being found? The days that followed the confirmation were filled with verification and re-verification. Observatories around the world coordinated data to ensure no computational errors existed. The measurements were solid. Parallax confirmed interstellar origin, and spectrographs verified an unusual reflective profile that did not correspond to ordinary silicate or carbonaceous material. Once the data passed every redundancy check, 3. I-Atlas officially entered the global catalogue of tracked celestial objects. The process moved quickly because the protocols for such discoveries had matured since Oumuamua and Borisov. The Minor Planet Center distributed updated ephemerides every 12 hours. Data pipelines connected to NASA's Center for Near-Earth Object Studies automatically recalculated the orbit using fresh input from optical observatories, radar facilities, and space-based telescopes such as NEO-EYES. This level of global synchronization was rare but necessary. Objects with hyperbolic trajectories move fast, and each hour mattered for refining predictions. In the earliest phase, it was still treated as a standard object of interest, something to measure, classify, and archive. Teams ran compositional models using the observed magnitude and assumed density. They simulated potential origins from nearby stellar systems, tracing back possible travel paths using stellar motion data from Gaia Drive 3. The results suggested a journey that began far beyond the Sun's influence, likely tens of millions of years ago. But while orbital reconstruction looked elegant on paper, the data held inconsistencies that unsettled many. When the trajectory was integrated backward through time, it did not fit neatly into expected interstellar velocity distributions. It seemed to have entered the solar system at an angle slightly shallower than most ejected debris from known stellar populations. This deviation was small but statistically significant. For dynamicists, even small differences matter. It meant that either the object had been perturbed before arrival, possibly by an unknown gravitational interaction, or its velocity had changed along the way. Astronomers began to split into two perspectives. One viewed the discovery as an exceptional opportunity to study interstellar geology, a chance to analyze the chemical and structural fingerprints of another planetary system. The other saw it as an anomaly that challenged established orbital physics. Both sides agreed that more data were essential. The first radar attempt came from the Goldstone Deep Space Communications Complex in California. Using high-gain radar pulses, scientists aimed to derive a delayed Doppler image that would reveal size and shape. The return signal was minimal, far weaker than expected for a body of estimated magnitude. It implied that the surface was either unusually smooth or composed of a material with a low radar albedo, similar to polished metal or dense composite rock. The size estimate narrowed to between 130 and 160 meters in diameter, compact, but large enough to be significant. Spectral analysis from the Very Large Telescope added another puzzle. The reflected light contained narrowband features that did not match known silicate or carbon absorption lines. Some spectra suggested a partial metallic component. Others hinted at compounds not easily classified under existing mineralogical databases. The emission at 532 nanometers remained constant, indicating an internal or persistent source rather than reflective variation. International coordination reached a new level of precision. The International Asteroid Warning Network formed a dedicated task group to manage communication and data synthesis. Every observation was time-stamped and uploaded into a shared database. Algorithms modeled potential interaction points with Earth's orbit. Early projections showed no immediate collision risk, but the intersection distance was small enough to justify continuous observation for the scientists involved. It became an exercise in endurance. Nights blended into each other. Teams slept in observatory control rooms, waking to new updates from other hemispheres. Every recalculated orbit, every new line of code, pushed the model closer to an undeniable truth that the object's motion was subtly but persistently changing over time. The adjustments were minor, often fractions of a degree, yet too consistent to attribute to random noise. Those shifts forced modelers to re-examine their assumptions about non-gravitational forces. Radiation pressure, the effect of photons exerting momentum on small bodies, was tested as an explanation. For objects like Oumuamua, this pressure had been invoked to explain mild acceleration. But 3I Atlas was larger and denser. Radiation pressure alone could not account for the deviations measured. Even after adjusting for maximum reflectivity, the observed movement required an additional source of thrust. No jets or vents had been detected. Thermal emission scans revealed no asymmetry or signs of sublimation. There was no coma, no dust release, no exhaust. The surface temperature remained stable, consistent with inert material. Yet, each new data point confirmed that acceleration persisted. The transition from curiosity to high-level concern was gradual but evident. By the time the object crossed the orbit of Jupiter, international research coordination had become as structured as a mission control operation. Data managers synchronized observation windows. Optical systems were retuned. Proposals were submitted for follow-up time on Hubble and the James Webb Space Telescope. These observatories could capture infrared spectra, potentially revealing what no ground-based telescope could. At the human level, the scientists involved expressed a mix of discipline and apprehension. The work remained methodical, controlled, and careful, but conversations grew quieter. A pattern was emerging, and patterns in space rarely appear without cause. For now, 3I Atlas was still just a catalogued body, an entry in the ever-expanding list of cosmic visitors. But within its data lay a deviation that resisted explanation. The realization settled slowly. This was not just another detection. It marked a point where observation began to transition into interpretation. The question was no longer what it was, but why it moved the way it did. And that single distinction transformed a simple survey discovery into one of the most scrutinized astronomical mysteries of the decade. Inside NASA's Jet Propulsion Laboratory, the late-night hum of computers filled the air like a mechanical heartbeat. Screens glowed with orbital plots, velocity curves, and simulation loops that stretched endlessly into hypothetical futures. 3I Atlas was now more than a data point. It was a presence, the kind that lingered in thought even after the monitors went dark. Scientists who had once spoken in calm technical briefings now lowered their voices, choosing their words carefully, as though the walls themselves might carry their speculations outward. The first arguments began quietly over coffee, between shifts, but they soon became structured debates in conference rooms. The question was no longer about data integrity, but communication. How soon should the public be told that an interstellar object appeared to be adjusting its path? That models hinted, however faintly, at a possible Earth intersection? There were protocols for asteroid warnings, impact risk scales, even planetary defense simulations. But this was different. The equations worked, yet they described something that did not behave like anything those equations were designed to describe. At NASA's Planetary Defense Coordination Office, emails multiplied overnight. Draft reports were written, redacted, rewritten again. The language walked a delicate line. Scientific precision on one side, the weight of implication on the other. Non-gravitational acceleration detected. Trajectory requires continuous monitoring. These were technically accurate, but each phrase carried a subtext that everyone understood. The universe had sent something toward us, and no one knew why. Across the Atlantic, in ESA's operations center in Darmstadt, the same tension took hold. Teams that had long coordinated asteroid tracking with detached professionalism now spoke with uncharacteristic restraint. The data matched. There was no observational error. The first atlas was indeed moving in a way that suggested internal or external propulsion. It was faint, consistent, and directionally aligned toward Earth's orbital corridor. Meetings stretched into dawns. Philosophical questions began to mingle with scientific ones. Was it ethical to withhold incomplete data, even to prevent panic? Was it responsible to announce findings that might later prove benign? Some argued for transparency, that public awareness was essential for trust in science. Others warned that a premature announcement could ignite hysteria, overwhelm communication systems, and spread misinformation faster than truth could follow. In between the meetings, the human cost began to surface. Astronomers who had once studied distant stars now stared at the same patch of sky night after night, unable to look away. Some stopped sleeping, haunted by the thought that each new data stream might confirm their fears. A few withdrew from public engagement entirely. Colleagues described them as overabsorbed, lost in the numbers, unable to step back. For them, science had always been a sanctuary of order, where uncertainty could be tamed by equations, where the unknown could be turned into data. But this discovery disrupted that fragile equilibrium. The object was measurable, but its intent or the illusion of one was not. Every model suggested motion governed by physics, yet intuition whispered of something deliberate, a coherence that resisted chance. Night. Observatories across the globe continued to track its faint glimmer. The data kept coming, silent and precise. Its light curve remained stable, no flicker of rotation, no chaotic tumbling that natural bodies display. It moved cleanly, efficiently, like a vessel rather than a rock. Of course, that was speculation, not science. But speculation is what scientists turned to when data grew cold and meaning became uncertain. NASA's internal forums filled with technical threads, equations, orbit revisions, theoretical explanations. But in private messages, the tone was different. Some confessed unease, others described vivid dreams of distant lights or strange sounds echoing from radio static. Sleep deprivation, perhaps, or something else, a mind trying to process a universe that suddenly seemed aware of its observers. In closed-door briefings, senior officials reviewed communication strategies. Draft press statements were written and locked behind restricted access. Each sentence was weighed like a moral decision. How do you tell the world that something is approaching when every model agrees but no one understands why? The discussions turned ethical, even philosophical. Some invoked the duty of scientists as stewards of truth. Others warned that the truth, in this case, was still undefined. The moment the first classified report used the phrase targeted trajectory, everything changed. It wasn't meant in a literal sense. The term referred to the statistical narrowing of the orbital path, but language carries power. Once the words were spoken, they lingered. Even those who knew better began to feel the gravity of their implication within the corridors of power. Outside the scientific community, the information began to spread quietly. Government liaisons were briefed, defense agencies notified, not because of confirmed danger, but because of uncertainty itself. History had shown that humanity feared ambiguity more than threat. Meanwhile, the people closest to the data, the astronomers, engineers, and analysts found themselves caught between fascination and dread. They were trained to observe without emotion, yet emotion found them anyway. Wonder, fear, hope, all blending into a kind of reverent disbelief. Some looked up at the night sky not as scientists, but as witnesses. Every new data point, every recalculated frame, deepened the same realization. The line between observation and participation was beginning to blur. Humanity had always been the watcher, the species that studied the cosmos from the safety of distance. But now the cosmos seemed to be watching back, closing that distance, one precise trajectory at a time. And so, in the dim light of a control room, beneath the glow of silent monitors, a quiet question began to echo among those who had first seen its approach. It was not written in any report or formal statement. It was whispered, as though spoken aloud might give it weight. What if we're not studying it? What if it's studying us? As the weeks passed, the crisis management structure around 3I Atlas solidified. A joint operations task force was formed, a collaboration between NASA, ESA, and several independent observatories under the International Astronomical Union. Their goal was to maintain objectivity, to keep science ahead of speculation. But in truth, the tension between data and narrative had already begun to fracture the community. Every new observation was no longer just a scientific measurement. It was a political and psychological event. Tracking stations in Hawaii, Chile, and South Africa continued to refine its path. The uncertainty window began to shrink, narrowing the potential outcomes of where 3I Atlas might pass. Normally, such refinement brought relief. But in this case, it only made the pattern clearer, its course aligned to precisely with Earth's orbital plane, as if the object had been programmed to follow the same invisible road our planet traveled each year around the Sun. Analysts in mission, control rooms cross-referenced the data dozens of times, hoping for error. They rechecked sensor calibrations, atmospheric corrections, optical distortions, anything that might explain away the precision. But the corrections only made the line sharper. The acceleration persisted. There was no visible outgassing, no debris tail, no radiation burst that could suggest a natural mechanism. Its consistency defied random behavior. For the scientists, the focus shifted from what it was to how it moved. The models grew complex, multivariable simulations accounting for radiation pressure, thermal inertia, gravitational drag from outer planets, even minute magnetic interactions. None of them fit perfectly. The trajectory still required a force vector unaccounted for by known physics. Not a large one, barely measurable, but consistent. That constancy was what disturbed them most. Nature fluctuates. Mechanisms stabilize. Inside NASA's Goddard Space Flight Center, proposals emerged for a dedicated probe mission. A modified intercept concept, based loosely on the DART program and New Horizons technology, was drawn up within days. Theoretically, a high-velocity craft could reach the object within months, if launched immediately. But funding, logistics, and orbital mechanics stood in the way. By the time a spacecraft could be ready, 3I Atlas might already be inside the inner solar system. Meetings with the Department of Defense grew more frequent. The dialogue remained cautious, framed around planetary defense preparedness and space situational awareness. Yet behind every formal term lay an unspoken question. What if this was not a natural body? Some military analysts quietly proposed radar tracking and signal interception tests. Others warned that active probing might be interpreted as engagement, a word that had never been applied to an interstellar object before. Publicly, nothing was said. The nightly news focused on more terrestrial concerns. The object's official classification remained interstellar visitor under observation. But within encrypted channels, a parallel language evolved. Words like approach, corridor, behavioral anomaly, and signal variance began to appear in technical memos. Engineers and astrophysicists who once dealt in probabilities now found themselves discussing intent. Not everyone agreed that silence was sustainable. Several prominent astronomers argued that the longer the data remained restricted, the more damaging the eventual revelation would be. They recalled the communication failures during the early days of Oumuamua's detection, how secrecy had fueled wild speculation online. But the agencies overseeing 3I Atlas weighed those risks differently. Panic, once triggered, could not be contained, and still the object moved, slowly, steadily, almost elegantly, across the void. With every passing day, it grew slightly brighter, its reflection curve suggesting an irregular surface geometry, not smooth, but fractured, as though layered or segmented. Some speculated it might be rotating very slowly, with one side reflecting more sunlight than the other. Others insisted the pattern showed controlled orientation, a stability unknown in naturally tumbling bodies. Radio telescopes were aimed toward its path. They detected nothing. No emissions, no signals, no modulated frequencies. Silence, absolute and total. That silence was in many ways worse than noise. It left every possibility open. If it was inert, it should behave like debris. If it was active, then its silence could be deliberate. Behind closed doors, psychologists were brought into advisory meetings, not to interpret the object, but to assess the human factor, how those studying it were reacting. Reports noted increased anxiety, insomnia, a sense of existential detachment among certain research teams. Long exposure to uncertainty, especially on a scale that challenges humanity's self-perception, was beginning to take a measurable toll. Some scientists requested transfers. Others buried themselves in work, finding focus in the precision of data that refused to offer meaning by the second month of observation. The debate shifted again. The new question was no longer if it would intersect Earth's orbit, but when. Projections varied by days, depending on models. But the convergence point was unavoidable. The object would pass within the vicinity of Earth's orbital track within the next 14 months. That proximity would allow observation at unprecedented resolution. For many, it was a scientific opportunity unmatched in history. For others, it was a reason to prepare for contingencies they could barely define. Even the language of official communication began to evolve. Object of interest became object of concern, not a declaration of threat, but an acknowledgement of uncertainty. Internal memos circulated recommending coordination with global observatories to maintain transparency, a preemptive effort to unify the narrative once the inevitable public recognition occurred. But outside the walls of the agencies, the first hints of awareness had already begun. Amateur astronomers posting images online noticed an unfamiliar point of motion near the outer edge of telescope detection limits. Within niche forums, discussions began, faint data trails matching publicly available orbital predictions. Slowly, word began to spread. For the organizations tracking it, the timeline had accelerated. They no longer controlled when the world would know, only how it would find out. Scientists faced a double burden: the obligation to remain objective, and the awareness that the truth might be larger than their understanding in the end. All the data converged on the same inescapable reality. 3I Atlas was inbound. Its motion was not random. Its silence was not empty. Every number, every observation, every recalibration pointed to the same conclusion. Something from beyond the stars was approaching with purpose, and humanity was running out of explanations to contain what that meant. At first, the approach of 3I Atlas was treated as a purely scientific phenomenon. The data flowed in quietly, processed through deep sky imaging arrays and ground-based optical networks. Yet, as the object moved deeper into the observational range, the clarity of its reflection began to reveal something that defied casual explanation. Across multiple nights of exposure, astronomers noted a consistent modulation in brightness, a pattern of light and shadow that repeated with mathematical precision. The conclusion was unmistakable: the object was rotating, and it was doing so in a stable, almost engineered rhythm at Mauna Kea, where the atmosphere thins into near silence. The Subaru telescope captured the first high-resolution composite. It revealed a faint green halo surrounding a dark core, an optical echo of its spectral signature first reported by Atlas. The light wasn't uniform. It shimmered, almost polarized, as though interacting with a surface unlike any asteroid or comet previously observed. When radar arrays were aimed at it, both from Arecibo's archives and new attempts from Goldstone, the signals returned nothing. They vanished into static, absorbed or redirected, suggesting a surface unusually resistant to radio reflection. It was as though the object swallowed every question humanity threw toward it. Spectral analysis deepened the mystery. Using reflected sunlight, spectrometers across Chile and Arizona mapped the object's chemical composition. It bore traces of nickel and magnesium common to many metallic asteroids, but the ratios were wrong. The absorption lines implied alloys that did not exist in any catalogued celestial body. There were discrepancies too subtle to dismiss as noise. One model proposed that its outer layer could be composed of nickel iron fused with an unknown dense lattice, one capable of refracting electromagnetic energy in an almost organized pattern. The data fed into simulation models at the European Southern Observatory. Thousands of origin scenarios were tested: ejected planetary debris, the fragmented core of a dead exoplanet, or perhaps the remains of a moon once bound to a wandering star. Each simulation broke down under scrutiny, for its velocity, density, and reflective characteristics to align. The object would have needed to form under conditions not yet observed in any natural astrophysical environment. A small group of independent researchers began to explore a more radical hypothesis. If its behavior could not be explained through natural mechanisms, perhaps it was artificial. Not a spacecraft in the traditional sense, but a relic, a structure adrift for eons, built by an unknown intelligence. Such speculation had always been part of scientific discourse, especially after the debates surrounding our. But this time, the evidence pressed harder. The symmetry of its light curve, the coherence of its orientation, the persistent silence of its radar profile, all combined to paint a picture that resisted random explanation. NASA's Jet Propulsion Laboratory revisited archived mission data from Voyager and Pioneer, two of humanity's own emissaries to the stars. The resemblance was unsettling. The rotational stability of 3I Atlas mirrored the spin calibration once used to maintain spacecraft equilibrium. Its reflective modulation was not unlike the behavior of metallic components in distant sunlight. For those who had spent decades designing human-built probes, the parallels were unmistakable. The idea that something could be crossing into our solar system, bearing the same mechanical signatures, humanity had invented for its own survival in the void, was not easily ignored. The deeper the investigation went, the more the object seemed to defy classification. Its albedo varied inconsistently, shifting between surfaces that absorbed light completely and those that scattered it like crystal. Some theorized a thin crust of carbonized material layered over metallic ridges, perhaps an ancient hole, worn smooth by countless collisions and cosmic erosion. Others speculated about adaptive materials, self-healing composites, or magnetic shielding, all theoretical technologies once proposed for interstellar travel. None of it could be proven, but the patterns were there, embedded within the data, waiting for someone brave enough to interpret them. As 3I Atlas moved inward, deep space radio dishes at the Allen Telescope Array began scanning for narrowband emissions. The search covered thousands of frequency channels, from microwave bands to deep radio silence. Nothing emerged. No structured signal, no digital sequence, not even a random burst. For many, this confirmed its natural origin. For others, the silence only strengthened the opposite argument that an intelligence capable of sending such an object might have no reason to communicate in human terms. Historical parallels surfaced. In the late 20th century, when Voyager 1 and 2 left the solar system, each carried a golden record, a fragile archive of human sound and image meant for whoever might find it. The decision to send those records had been philosophical as much as scientific. It was an act of faith that something, somewhere, might listen. Now, decades later, humanity found itself on the opposite side of that equation. The possibility that something had sent a message of its own, not through sound but through presence, hung in the silence between observatories. Within academic circles, the discussions turned cautious. Some papers avoided definitive language altogether, describing 3I Atlas as a hyperbolic, metallic anomaly with spectral irregularities. Others were less restrained, framing it as a potential non-natural interstellar construct. None of these phrases could be verified, but they marked a shift, a moment when the language of exploration began to merge with the language of fear. The emotional atmosphere among researchers reflected that tension. Curiosity warred with unease. Teams who had once celebrated the thrill of discovery now spoke in whispers about intent. What if the object wasn't a message but a mechanism? What if its approach was not observation but function? No one could say what kind of civilization might have built it, or how long ago. The distances between stars erode all assumptions about time. Even if the structure was ancient, it could still carry systems dormant for millions of years. In one internal report, a scientist at ESA wrote a simple line that would later circulate through both agencies and online. Communities, we built Voyager to send our story to the dark. What if the dark has just sent its reply? That question changed the tone of the entire investigation. Every new measurement became more than data. It became interpretation. The object no longer belonged to the cold catalogue of cosmic debris. It had entered the realm of human meaning. And in that realm, science met something larger than itself. The realization that perhaps the frontier was no longer about reaching the unknown, but about facing it as it came closer. As 3I Atlas crossed the 4.5 astronomical unit mark, positioned between Jupiter's orbit and the asteroid belt, the global network of observatories intensified its observation cycle. Data sharing among nations became daily protocol, with synchronized imaging runs designed to capture its every movement. Infrared arrays were engaged to study its thermal output, and the readings only deepened the mystery. The surface temperature of the object remained unexpectedly stable, even as it moved through varying distances from the Sun. A typical asteroid of comparable size would have exhibited thermal flux heating up and cooling down as it rotated. 3I Atlas did not. Its temperature curve was flat, as though internally regulated or shielded from solar radiation altogether. In the analysis labs of JPL teams began exploring thermal equilibrium models to explain the anomaly. One proposal involved an ultra-dark material, perhaps carbon nanotube-like in structure, absorbing radiation evenly across its surface. Another suggested active internal heat distribution, a mechanism impossible for a non-technological body. The same conclusion kept reappearing. Something was maintaining balance. The silence surrounding these findings grew deliberate. Officially, reports stated that unusual albedo patterns continue to challenge current models. Privately, scientists knew those words were an understatement. Magnetometric readings presented another problem. As the object approached the heliocentric magnetic plane, magnetometers aboard the Solar and Heliospheric Observatory detected minute distortions inconsistent with natural phenomena. The field oscillations were too regular, too cleanly modulated. Some believed the readings might be the byproduct of a rotating ferromagnetic structure, perhaps residual magnetization from its formation. Others began to note the timing. The oscillations correlated with the object's rotation, suggesting a link between motion and field variation. It wasn't random interference. It was behavior. The SETI Institute launched a new series of coordinated listening sessions, sweeping across bands not typically associated with natural emission. They broadened their search to subharmonic frequencies, microwave reflections, and pulse gaps. Over thousands of recorded hours, no artificial signal appeared. But what caught their attention was something subtler, a faint, rhythmic dip in background cosmic noise whenever the object passed within a certain alignment relative to the Sun. It was as though its presence disrupted the quiet hum of the interstellar medium itself. The data was not conclusive, but it was persistent to rule out instrumentation error. Independent teams at the Atacama Large Millimeter Array repeated the measurements. The anomaly was real. The explanation, however, was not. It didn't emit energy. It seemed to shape it, bending and damping the electromagnetic field in a narrow cone around its path. The effect was minuscule but measurable, like the wake behind a ship traveling through an invisible ocean. Parallel efforts turned to the question of structure. Using light curve inversion methods, researchers reconstructed a rough shape model. It appeared elongated, an ovoid body roughly 200 meters in length and 90 in width, rotating on a slow axis tilt. Surface roughness readings indicated fractured planes and ridges, perhaps the remnants of impacts or layers built over time. Yet the rotation remained stable. No sign of precession, no chaotic tumbling. For an object of that irregularity, such balance bordered on mechanical precision. In one notable analysis from the Max Planck Institute for Astronomy, a researcher drew comparisons between the observed rotation and the spin dynamics of engineered probes. Artificial satellites are often stabilized through gyroscopic momentum or internal counterweights. Natural bodies, by contrast, drift and tumble under external forces. The paper stopped short of any explicit claims, but the comparison was unavoidable. If the object was natural, it behaved like something designed. NASA's Planetary Defense Coordination Office continued to monitor for potential hazards. While there was no immediate impact threat, the precision of its alignment with Earth's orbital path was alarming. Even a non-collisional pass could disrupt satellites or space-based assets if gravitational interactions were significant. Simulations suggested a near pass within several million kilometers, close enough for direct observation, but close enough also to remind everyone that the unknown was moving within reach. During these months, new data came from the James Webb Space Telescope. Though not originally intended for near-field tracking, it was temporarily redirected for spectral analysis during a window of high visibility. The results arrived quietly, but caused unease among senior scientists. In the mid-infrared range, Webb detected patterns that did not match any known mineral or molecular composition. The surface absorbed and re-emitted light in narrow thermal bands, almost like tuned filters. The readings hinted at microscopic structures that manipulated radiation intentionally, not unlike metamaterials theorized for cloaking or signal redirection. The implications of those findings demanded verification, and yet few were willing to publicize them. The risk of misinterpretation was enormous. In press releases, the data was summarized as unusual reflectivity with potential metallic organic layering, but the internal summaries circulated among specialists used another phrase: engineered scattering behavior. It was a cautious way of acknowledging what everyone had begun to suspect. If 3I Atlas was a fragment of something built, then its origin predated recorded history, parallel to the technical work. Historians and astrobiologists revisited the timeline of interstellar travel concepts. They reviewed ancient human efforts, Voyager, Pioneer, New Horizons, and the optimism that once surrounded the idea of communication through machines. Those projects had been designed to represent humanity in the vast unknown. The golden record, the engraved plaques, all messages meant to outlive the species that made them. Now, the reflection was reversed. The message had returned, though no one knew who sent it or what it carried. In theoretical astrophysics circles, discussions turned to longevity. Could an object survive interstellar travel for millions of years without disintegration? Under ordinary conditions, no. Cosmic radiation, dust impacts, and thermal stress would degrade any structure beyond recognition. To remain intact, 3I Atlas would have required self-repairing mechanisms or protective coatings beyond current human technology. A few proposed that it might not be solid at all, that its apparent stability could conceal an adaptive interior, a framework of self-organizing particles maintaining coherence through magnetic or quantum interactions. As those hypotheses grew bolder, so did the questions surrounding human readiness. If this object had been launched long before human civilization even formed, what did that say about the age and scope of intelligence in the galaxy? If it was an artifact, it had crossed light years of emptiness without failing. Its silence could be a result of damage, dormancy, or something else, something waiting for the right environmental trigger to awaken. Governments began funding contingency research. Small-scale projects examined the potential for non-invasive observation techniques, studying how to image or intercept without interference. There was discussion of deploying a probe along its projected path, a maneuver similar to the Parker Solar Probe's orbital assist sequence. But the logistics were unforgiving. The trajectory required speeds beyond current capacity, and even the fastest intercept would arrive after the object had already passed. Humanity would have to watch from a distance by now. The term artifact had crept into internal communications, though never publicly acknowledged. The official lexicon remained cautious. Object of anomalous behavior, unclassified interstellar body, subject of ongoing analysis. Yet behind every line of scientific restraint was a growing recognition that this discovery had changed the narrative of space exploration entirely. Humanity was no longer the sole sender of signals. For the first time, it might be the receiver. The final report of that observation phase concluded without conclusion. The object was real. Its movement was precise. Its surface was unlike anything known, but its purpose remained undefined. The data offered no voice, no command, no origin point, only the undeniable presence of something that should not exist, and yet did, and so, while the telescopes kept tracking and the instruments kept listening, the world's scientists could only confront the paradox at the heart of discovery itself, that sometimes the greatest truths do not arrive with answers, but with silence that cannot be ignored, out beyond the orbit of Mars, where sunlight thins into a pale echo and gravity itself begins to loosen its grip. The object known as 3I Atlas continued to move with impossible precision. Each observation refined its trajectory, yet none could explain it. The motion was not chaotic, not the wandering drift of a rock tossed through space by chance. It was deliberate, constant velocity with subtle, periodic corrections, as though responding to forces invisible to human understanding. Physicists began to admit what their equations had been hinting at. This was not a Newtonian body. Its acceleration did not match the sum of gravity, radiation, or solar wind. Something else was guiding it. At first, the explanations stayed conservative. Solar pressure, perhaps. Pushing against a highly reflective surface, the same phenomenon that moves cometary dust and tiny interstellar grains. But the math refused to cooperate. The object's reflectivity was too low, its mass too great. And yet its deviation from expected trajectory was precise, sustained, and rhythmic. That left theorists staring into a new kind of question, one that bent the edge of physics into speculation. Could a structure, without engines or exhaust, manipulate the quantum structure of space itself to move? Could it surf on the vacuum fluctuations that underlie reality, a quantum sail operating on principles still theoretical even in human laboratories? In meeting rooms and late-night video conferences, the boundaries of scientific caution began to blur. Astrobiologists joined the discussion, not with proof, but with frameworks for the unthinkable. What if the object wasn't alive, but still capable of decision? What if it was built to react, a dormant intelligence coded into matter itself, guiding it across the gulfs of time? The idea of agency without biology emerged. A machine that could adapt without thought, evolve without genes, and navigate without awareness. Something designed to survive eons by following a set of rules that even its makers might have long forgotten. In the clean rooms of simulation centers, engineers fed the data into AI systems trained to reconstruct possible internal architectures. The models began to imagine what human minds could not visualize: hollow networks of microstructures, perhaps lattice-like shells that redistributed solar and magnetic energy through coordinated vibration. Some iterations resembled photonic crystals, capable of redirecting light for propulsion. Others resembled fractal resonators, hypothetical systems able to couple with the quantum field, exchanging momentum with space itself. It was speculation at the frontier of reason, but the consistency between models was eerie. They all converged on one conclusion: if such a mechanism existed, it would explain the motion perfectly. NASA's own theoretical physics group, working quietly under limited circulation, revived concepts once dismissed as science fiction. The Mach effect thruster, once a fringe pursuit, was re-examined. Could inertia itself be manipulated by altering the energy density of a system? If so, 3I Atlas could, in theory, accelerate without fuel, using the structure of space-time as a reaction medium. No exhaust, no emissions, no decay. Just motion, persistent and silent. For decades, science had searched for evidence of technology beyond Earth, through signals, radio bursts, transmissions, repeating patterns of light. But 3I Atlas offered something subtler and far more unsettling: technology expressed as behavior, not in communication, but in physics. The universe was not speaking, it was demonstrating. Astrobiologists began to frame new definitions of life. Some argued that agency could exist in material systems far removed from carbon chemistry. If matter could encode purpose through arrangement, resonance, or feedback, then even a rock, under the right construction, could be a messenger. They called it mechanical sentience, not consciousness as humans understand it, but a capacity for ordered reaction to disorder, for persistence through adaptation. A machine that doesn't think, but endures. As the debate grew, another question surfaced, one far less technical and far more existential. If this object was not natural, then why was it so old, so eroded, and yet still functional? Its journey must have begun long before human civilization emerged, perhaps long before Earth had even cooled from its molten youth. If it had been launched, then by whom? If it had been drifting, then toward what? And if it was guided by pattern, field, or will, then whose? Theorists from quantum mechanics to philosophy of mind converged on a common admission: the categories were insufficient. Physics could describe movement, chemistry could describe material, but neither could describe intention in an object that exhibited no biology and no message. 3I Atlas was forcing science into territory where data became indistinguishable from myth. Within this uncertainty, a new discipline began to coalesce: non-biological astrobiology. The study of intelligence expressed through physical law rather than organic life. Its founding principle was radical yet elegant: that the universe itself might serve as a computational medium. and some civilizations may have learned to shape it directly, leaving behind artifacts that are not machines, but phenomena. Across observatories, the tracking continued. The datasets grew denser, but the mystery did not shrink. Every new measurement only confirmed the same contradiction, that the object behaved as though aware of its environment, yet betrayed no hint of communication or energy output. It adjusted, but not randomly. It held course, but not rigidly. It was as though it knew the difference between chaos and stability, and chose the latter. In an unpublicized roundtable hosted by ESA, one scientist summarized what the data had forced them to confront. He said, quietly, "If this is natural, it's the most unnatural natural object we've ever found." The room stayed silent after that. For all the language of science, there was no better phrasing. As the days passed and 3I Atlas drew closer to the inner solar system, the instruments would continue to follow its progress. But beyond the numbers, something deeper had shifted. Humanity had spent centuries believing that understanding the cosmos meant reducing it to laws. Now, standing before an object that obeyed those laws in ways no equation could predict, science had reached its own horizon, the edge where curiosity becomes awe, and discovery begins to resemble faith. Observations deepened as 3I Atlas entered the range of higher resolution optical arrays. Telescopes stationed in Chile, Hawaii, and Spain coordinated continuous monitoring, exchanging terabytes of visual and spectroscopic data. What emerged from the raw imagery was unsettling in its precision. The object rotated on an axis inclined roughly 38 degrees, maintaining perfect periodicity. Its spin rate did not vary with solar torque, radiation pressure, or tidal interactions. Normally, even a small irregular body in interplanetary space exhibits minute fluctuations in spin caused by asymmetrical heating or collisions with microdebris. 3I Atlas did not. Its stability defied the statistical chaos that defines natural motion. Radar teams from Goldstone and Arecibo attempted active scanning, but the echoes returned distorted or absent altogether. The object absorbed rather than reflected, suggesting a surface composition inconsistent with standard asteroid or comet models. The reflectance curves pointed toward an unknown alloy, a compound that appeared metallic yet showed spectral absorption bands closer to silicate structures. Under normal analysis, this should be impossible. Metallic surfaces reflect, silicates absorb. 3I Atlas did both. When modeled, the surface behaved like a metamaterial, a theoretical configuration capable of manipulating electromagnetic energy at the nanoscale. Material scientists reviewing the data noticed that the reflected spectrum contained faint anomalies in the near-infrared band, indicating possible trace elements of magnesium, nickel, and an unclassified absorption feature that didn't correspond to any known terrestrial or cosmic compound. The ratio between these metals implied a refined structure rather than a natural alloy. Nothing about it suggested formation in a stellar nursery or as the remnant of planetary collision. It seemed assembled, or at least processed, shaped by conditions not found in nature. Computer simulations were run across supercomputing clusters. The objective was to recreate an object that could display identical motion and composition using known physical laws. Thousands of runs failed to converge on a single, plausible, natural origin. The only configurations that matched the trajectory and non-gravitational acceleration required internal mechanisms, variable mass, redistribution, or directed energy propulsion. Both implied design. the debate fractured the scientific community. At NASA's Jet Propulsion Laboratory, modelers leaned toward a natural explanation, perhaps an exotic fragment ejected from a system near a magnetar, its structure altered by extreme radiation. ESA's Deep Space Dynamics Group, on the other hand, began to argue that this was no random ejection. The consistency in rotation, the uniform thermal emission, the lack of outgassing or erosion all pointed to something engineered, even if only incidentally. It could be ancient, derelict, a probe from a civilization extinct before Earth ever formed. Or it could be the relic of a process, an automated fragment of cosmic evolution itself. Astrobiologists revisited earlier assumptions about what defines life and technology. Could an object function as both? Could evolution occur in metallic systems under different environmental constants? Laboratory studies on self-assembling nanoalloys had shown that order can emerge from energy gradients. If that same principle scaled to interstellar conditions, then perhaps life was not confined to cells and biochemistry, but could arise from magnetism, crystal symmetry, and conductive geometry. NASA's Planetary Defense Office remained publicly silent, but leaked internal memos revealed growing unease. The object's trajectory continued to adjust, subtly, always optimizing, avoiding minor gravitational interactions that would alter its timing. It was as though 3I Atlas navigated through a predictive model of the solar system rather than responding Its path suggested anticipation, not coincidence. Quantum physicists began proposing theoretical mechanisms for propulsion that required no chemical or mechanical thrust. One proposal was the dynamic Casimir effect, the possibility that vacuum fluctuations could be converted into kinetic energy by oscillating conductive boundaries at relativistic speeds. If 3I Atlas employed such a system, it could, in theory, use spacetime's own energy density for motion. No fuel, no decay, just sustained momentum through quantum exchange. Engineers studying solar sails found unsettling parallels. When simulations modeled ultra-thin, reflective materials under intense photon pressure, the acceleration profiles resembled early readings from 3I Atlas, yet the directionality was wrong. The object's acceleration opposed what solar pressure would produce. It wasn't being pushed by sunlight. It appeared to use it. At Los Alamos, physicists fed the object's trajectory data into a reinforcement learning algorithm to search for an underlying behavioral pattern. The program's output identified statistical signatures of optimization. The object's route seemed to minimize energy expenditure over time. In other words, it behaved as though it was following a goal function. No one could define what that goal was. Public disclosure lagged behind the internal scientific reality. What had started as an unusual object from another star system had become a full-scale anomaly, one that challenged the distinction between artifact and natural formation. Committees formed around how to release data without igniting public panic. Scientists, trained to dismiss sensationalism, now debated vocabulary. Should it be described as engineered, structured, or unknown class interstellar body? Each term carried different political weight. At the theoretical edge, a growing minority proposed that 3I Atlas could be a probe, not in the traditional sense, but as a passive system, a device that interacts with its environment only through physics, a kind of data recorder or self-guided archive, traveling for millions of years until encountering another region of organized matter, in this case, the solar system. Its lack of signal transmission would then make sense. It did not need to communicate in electromagnetic terms. Its message might lie in its behavior, in the way it demonstrates the physics of its makers. Philosophers of science entered the conversation, comparing 3I Atlas to a cosmic mirror. They suggested that humanity's attempts to interpret it might reveal more about human limits than about the object itself. Every hypothesis forced reflection on what science considers possible propulsion without exhaust, control without life, purpose without consciousness. As the data accumulated, the tone within research institutions grew colder, more clinical. Scientists were no longer searching for discovery, but for containment of uncertainty, containment of implications. The universe, for the first time in modern memory, was presenting an equation that could not be solved by expanding knowledge, but by redefining it. In the months that followed, one conclusion gained quiet consensus. If 3I Atlas was natural, it would rewrite the laws of astrophysics. If it was artificial, it would rewrite humanity's place in the cosmos. Either way, it had already achieved something extraordinary. It had forced civilization to admit that science itself had reached its event horizon, a place where observation stops explaining and begins only to remind that something far greater is watching back in the weeks that followed. As 3I Atlas crept closer to the inner solar system, the atmosphere within the scientific community shifted from astonishment to methodical restraint. The first wave of hypotheses came from the mainstream. The astrophysicists and dynamicists trained to see anomalies as puzzles, not portents. For them, the object's strange acceleration could still be explained by familiar forces, if only the data were interpreted correctly. NASA's Solar System Dynamics Division proposed that the faint deviations in its trajectory might arise from outgassing, the slow release of volatile compounds heated by sunlight, much like a comet shedding vapor as it approaches the sun. If 3I Atlas carried frozen carbon dioxide or ammonia beneath a dust-encrusted crust, then small, uneven jets of sublimating material could provide the delicate thrusts observed in its motion. The idea was elegant, conservative, and testable, but the data disagreed. No visible jets were recorded, no coma formed, and no trace gases appeared in the spectrum. For a comet-like model to hold, the emissions would need to occur without leaving any optical signature, an impossibility under current physics. Propulsion engineers within NASA's Glenn Research Center examined solar radiation pressure as another source of acceleration. Perhaps, they argued, 3I Atlas was composed of an ultralight material, something akin to carbon foam, large in area but low in mass. Photons striking such a surface could produce measurable thrust, mimicking an artificial sail. Calculations showed that this could account for some of the non-gravitational effects, but the composition required to make it work would render the object too fragile to have survived interstellar travel. Its observed density and reflectivity contradicted this scenario entirely. Attention then turned toward gravitational anomalies. A few theorists speculated that Jupiter's complex gravitational field might have nudged the trajectory subtly over time, creating the illusion of autonomous course correction. Others invoked solar wind turbulence, fluctuating streams of charged particles that could in principle exert uneven pressure on a highly magnetized body. These explanations were physically sound but lacked the precision needed to replicate the observed pattern. The corrections 3I Atlas performed were too consistent, too sustained, as if directed by a continuous feedback loop. As models failed one after another, statistical arguments began to take precedence. Could the alignment with Earth's orbital plane simply be coincidence? After all, in an infinite universe filled with countless random trajectories, a few would naturally intersect our path by chance. Astronomers at the European Southern Observatory ran Monte Carlo simulations, millions of random trajectories, modeled over cosmic timescales. The probability of such a near-perfect alignment was not zero, but it was vanishingly small. Out of 10 million simulated interstellar arrivals, only a handful approached Earth's orbit with similar precision. Still, the cautious voices of science urged restraint. Unlikely did not mean impossible. Mainstream astrophysics clung to the principle that extraordinary claims demand extraordinary evidence. The story of Oumuamua loomed large in every discussion, the first interstellar object ever discovered, whose strange shape and motion had briefly ignited speculation about extraterrestrial engineering. Years later, no definitive evidence emerged to support that idea. In retrospect, the field had learned a lesson in humility. To leap from anomaly to intelligence was to betray the very foundations of scientific inquiry. 3I Atlas, despite its behavior, deserved the same discipline. Committees formed within NASA, the European Space Agency, and the International Astronomical Union. Their statements were careful, measured. Non-gravitational acceleration consistent with outgassing. Read one early summary, despite the absence of any detected gases. Further observation required. Every official line reaffirmed skepticism as a virtue, a shield against the human tendency to fill cosmic silence with meaning. At Caltech's Jet Propulsion Laboratory, teams continued to refine dynamical models using updated positional data. Each recalculation, each new orbital fit narrowed the uncertainty but widened the mystery. The vector remained subtly adaptive, not random. In simulation after simulation, when solar wind, radiation, and gravitational drag were all accounted for, a residual remained, a persistent acceleration of unknown origin, directed not away from the Sun as expected, but inward, toward Earth's orbital path. Still, the most conservative researchers resisted the pull of speculation. They reminded one another that science advances through patience, not wonder. Space is full of outliers, comets with fractured cores, asteroids that spin faster than physics should allow, binary systems whose gravitational waves ripple through the cosmos. Anomalies do not always imply intent. The great danger was to mistake the unfamiliar for the intelligent. In that spirit, a new working group was formed, the 3I Atlas Non-Gravitational Dynamics Task Force. Its mandate was clear: to model every plausible natural mechanism capable of producing the object's motion. Specialists in thermodynamics, plasma physics, and celestial mechanics joined forces, constructing ever more complex simulations. Each attempted to reconstruct the faint push and pull of unseen forces: sublimation, micro-impacts, magnetic coupling, and thermal recoil. But as the data improved, the explanations narrowed. Nothing purely natural could sustain such coherence for so long. Within closed meetings, the language began to shift. Words like correction and stabilization slipped into official notes. Even those who dismissed the possibility of design could not ignore the appearance of control. And yet, no signal was detected, no pulse or emission indicating technology. What remained was motion, silent, measured, deliberate. Mainstream science stood at an impasse. To maintain skepticism was to uphold rigor. To ignore the evidence was to betray it. 3I Atlas sat at the intersection of both, a mirror reflecting the discipline's strength and its limitation. The The same caution that guarded truth now also guarded against revelation. In the end, the consensus, fragile but public, declared 3I Atlas, a non-cometary interstellar object exhibiting weak but sustained non-gravitational acceleration. It was a statement of facts and nothing more. But beneath its technical phrasing lay a quiet discomfort. For behind the graphs and equations, one question still hung unanswered in the air. How long could coincidence continue to behave like intention? In the months that followed, the flow of data became relentless. Every observatory equipped to track faint, fast-moving bodies joined the collective effort. The Pan-STARRS survey in Hawaii, the Subaru telescope in Japan, the European Southern Observatory in Chile, and NASA's infrared instruments aboard NEOISE all contributed streams of measurements that refined 3I Atlas's position to an unprecedented precision. The object's path was charted against known celestial bodies with errors smaller than a kilometer. Yet the deviations persisted, consistent, directional, inexplicable. The more clearly scientists saw it, the less they understood. Data analysts at the Harvard-Smithsonian Center for Astrophysics re-examined the residuals that standard gravitational models could not account for. These were the small differences, mere fractions of a millimeter per second, between predicted and observed velocities. Normally, such discrepancies would vanish with improved modeling or new data corrections. But in this case, the deviations grew sharper, more defined, as if clarifying rather than dissolving. The vector of acceleration aligned increasingly toward a single plane Earth's orbital path. There were no signs of random perturbations, no irregularities that could be attributed to tumbling or internal venting. Whatever was influencing the motion seemed continuous, not chaotic. In parallel, material scientists turned their attention to the spectral readings. The faint green hue that gave 3I Atlas its recognizable signature came under deeper scrutiny when the data were corrected for solar scattering and Doppler shift. The reflected spectrum showed metallic peaks corresponding to nickel and magnesium, but at ratios not seen in typical meteorites or asteroids. A small but persistent signal at 520 nanometers suggested a complex mixture, possibly a crystalline alloy that had formed under non-terrestrial conditions. Laboratories running compositional simulations tried to recreate such a signature using known elements, but no standard mixture reproduced the observed intensity. This led to cautious speculation that the object might possess surface coatings or inclusions formed in environments outside of any known planetary chemistry. Mainstream institutions resisted sensationalism, but curiosity was growing. If 3I Atlas was natural, it represented a category of object unseen before, one that bridged the properties of rock, metal, and possibly engineered structure. Papers began to appear in preprint archives, each attempting to explain the same irregularities through established physics. Some proposed magnetically induced torque, that the object's internal structure might respond to the interplanetary magnetic field, producing minute thrusts. Others invoked electrostatic charging due to solar radiation, creating a subtle coupling between plasma flow and surface materials. Each idea worked mathematically in isolation, but none matched the full behavioral profile. Within NASA, teams were reminded of their guiding principle: no assumption without verification. The solar sail hypothesis, initially dismissed as fringe, was given a second look after new data hinted at reflective patterns too regular for an uneven surface. Theorists calculated that if 3I Atlas possessed thin, sheet-like components, perhaps layered, crystalline panels, the pressure of sunlight could indeed produce steady acceleration. But this required dimensions and tensile strengths beyond any naturally occurring material. A single structural imperfection would destabilize the motion. Yet 3I Atlas remained remarkably consistent, holding attitude as though maintaining a balance. At ESA's Space Situational Awareness Program, data scientists compiled all available readings into a unified trajectory map. When projected forward under standard gravitational influences, the path diverged slightly from observation after only a few days. When corrected for the unexplained acceleration, the prediction aligned perfectly for weeks. It was an outcome impossible to reconcile under known models of orbital mechanics. The parameters had to be adjusted manually, not computed, a correction of unknown origin compensating for an unknown cause.